All right, hi folks, this is Larry Mussolino. I wanted to record a short video here to help you with the Module 9 homework. And Alex, a few students were asking me questions about solving some of the examples, things like asymptotes and inequalities and things like that. So I thought I would record a video here, walk you through a few of these examples. Let me start here with number one. This one says find all real zeros. Well, really what they're asking you is when is this f of x equal to zero? That's what a zero is. So a zero is when f of x equals zero. So I'm going to replace f of x with zero and try to solve this equation. Well, anytime you have parentheses like this set equal to zero, you're allowed to set each parenthesis separately equal to zero. What that means is I could take this first parenthesis, set it separately equal to zero. Take this middle parenthesis, set that equal to zero. And take this last parenthesis, set that equal to zero. Now I can just solve each one of these equations separately. Here I'll divide both sides by -5. So that would get me x equals 0. Here I'll add 3 to both sides. That would get me x equals 3. Here I'm going to add 4 to both sides to get started. That's going to get me x squared equals 4. Well, I want to get x by itself. I'm going to take the square root of both sides. But when you take the square root of both sides like this, you have to put a plus or minus symbol in front of the square root of 4. On the left side, this square root cancels out the exponent 2. And on the right side, I can think of it as x equals plus or minus 2, because the square root of 4 is 2. Now I'll break this up into two separate equations, x equal 2, x equal -2. So really we have 4 answers here for the zeros. We have 0, 3, 2, -2. One thing to be careful about for this question is it says find all real zeros. That means you can't come up with any answers that are imaginary answers. What I mean by that is if you had a parenthesis that was, let's say, x squared plus 9 equals 0, right? Instead of x squared minus 4, let's say it was x squared plus 9. Well, you could subtract 9 from both sides and end up with x squared equals -9. But there's no real solution to this because if you were to take square root of both sides here, you would end up with an imaginary answer. So something like that, there would be no real zeros coming out of that. All right, let's look at another example. How about if we look at number, I'm going to try to do examples that are different from one another. So let me jump to number 5 here. I think was different. All right. So this is going to ask you to look at a graph and answer a bunch of questions. All right, let's go to the first question. It says, which intervals is the graph increasing? So let me look at this graph. Well, increasing means the graph is going uphill. It means uphill. So let me look at different parts of this graph and ask myself, where is the graph going uphill? Well, over here, yes, the graph is going uphill. Here, the graph turns to go downhill, so I'm not going to include that interval. Here, the graph is going uphill. Here, the graph is going downhill. Here's an uphill, downhill, uphill. So decreasing means the graph is going downhill, but increasing means uphill. So they're asking us for uphill. All right, well, it looks like, let me call this interval A here. Interval A is going to be -infinity to -7. We're talking about x values now. So I'm looking at the x values. So this interval here is going from -infinity to -7. Let me come here to this interval. This interval is going from -5 to -2. Again, we're grabbing x values. Okay, so we're calling this interval B. Let me come here, call this interval C. This looks like x equal 3 to 6. 3 to 6. And there's one more. I'll call this interval D over here. It looks like going from 8 to infinity. So 8 to infinity. So these are the 4 intervals where the graph is increasing. So what I would do is scroll down and pick those 4 intervals. Negative infinity, -7, -5, -2, 3, comma 6, and 8, comma infinity. Okay. Next, it says, at what x values does the function have local maxima? Well, maxima means, let me erase some of this. Maxima means the graph is reaching a peak. So let me label some of these points. So maxima, well, you can think of it as the word maximum, means a peak. You know, you can think of it as the top of the roller coaster. Well, here's a max, here's a max, and here's a max. Right? These points that I just circled all represent the top of a roller coaster, so to speak. So there's 3 maximums here. It looks like x equals 7, x equal -2, and x equals 6. What if they had asked us about minimums? Well, a minimum would be where the graph reaches a valley, like the bottom of a roller coaster. So this point would be a min. Here's another min, and here's another min. All right. Let's scroll down to the next question. It says, what is the sign of the leading coefficient, and which of the following is a possibility for the degree? All right, let's go to part C. So is it positive or negative, leading coefficient? Well, what I want to think about is just looking at the endpoints of this graph. So this graph kind of does something like this. I'm just looking at the ends. So it kind of goes down this way and then goes up over here. I know there's these dips and max and mins in between, but I'm ignoring those for this question. I'm just looking at the endpoints. When a graph does something like this that I just drew, or does something like this, the leading coefficient here is positive. If I flip these graphs around, and you could think of this as kind of like the y equal x to the 3 curve. You could think of this as the y equal x to the 2 kind of curve. So these are like the 2 fundamental curves you could think about here. If the graphs were flipped, so if I had a graph that did something like this, or a graph like this, here, these would be leading coefficient negative. So for example, this might be the graph of y equals negative x to the 3. This might be the graph of y equal negative x to the 2. Okay, so the answer here is for our graph, because our graph looks like this, the leading coefficient is positive for this example. All right, let me go to the last question. The last question said, which of the following is a possibility for the degree of the function? Well, to answer that, you have to look at how many max mins. So there's a rule that says the degree of the function, by the way, degree means the highest exponent on x. So if a function was, x to the 7 plus, etc., the degree here, we call this degree 7, because that's the highest exponent on x. Well, the degree of a function has at most, let's call it degree n, has at most n minus 1 max mins. So let me count up the number of max mins here. There's 1, 2, 3, 4, 5, 6. So there's 6 max or mins here. By the way, we call those extrema. Extrema just means where the graph is hitting an extreme, either a top or a bottom. Well, the degree has to be one more, at least one more than that. So this is going to be degree 7 or greater. Could be degree 8, could be degree 9. So I'm going to come down here and select the answer. We need degree 7 or larger. So I'm going to say 7 or 8 or 9. All right, so you count the number of max mins, and then the degree has to be 1 or more larger than that. Our example, we had 6 max mins. That means the degree has to be 7 or larger. All right, so that was a question that had a few parts to it. All right, let me go to another one. Let me go to number 7. All right, so this one says find all values of x that are not in the domain for this function. Well, domain really means the allowed values for x. So what values of x are you allowed to plug in? Well, let me think about the values of x you're not allowed to plug in. Well, you cannot divide by 0. That means I can't let this denominator equal 0. So to find numbers, I'll say find x values that are not in the domain. That's the question here. What values of x are not in the domain? To find x values not in the domain, set the denominator equal to 0 and solve for x. All right, let's do it. I'm going to take x squared plus 4x minus 32, set that equal to 0. Let me try to factor this left side here. I'm going to put an x in front. And now I'm looking for two numbers. You remember how to factor here? I'm looking for two numbers to put in these blue boxes. The two numbers have to multiply to negative 32, but add to positive 4. All right, so let me do a little bit of a logic puzzle here. We need two numbers for the blue boxes, where the two numbers have to multiply to negative 32, but at the same time add to 4. Well, I know if the two numbers have to multiply to negative 32, the numbers have to have different signs. One has to be positive, one has to be negative. How about 8 and negative 4? I think that might work, because 8 times negative 4 is negative 32. 8 plus negative 4 is positive 4. So I think that's it. X plus 8, x minus 4. Now I can set each parenthesis separately equal to 0. X plus 8 equals 0. X minus 4 equals 0. So x equal negative 8, x equal 4. These are the two answers to this question. So my answers here are negative 8, comma 4. If I plug in those values for x, I'm going to end up with a 0 in the denominator, which is not allowed because you can't divide by 0. All right, so for this question, what you should do here is set the denominator equal to 0 and solve for x. The top of the fraction plays no role in this question, so you could ignore the top of this fraction. All right, I'm going to keep going. All right, this one is similar, but it's asking us to write the answer as intervals. So let's do, there's two parts to this. So let's do part A. Part A says, what is the domain? Well, let me find the values not in the domain. Values not in domain. Really mean the x values not in the domain. Remember, for this, we set the denominator equal to 0. So x squared minus 4 equals 0. Add 4 to both sides here. That's going to get me x squared equals 4. Square root both sides. but you got to remember to put a plus or minus in front of the square root of 4. So x is plus or minus 2. So x equals negative 2, x equal positive 2. Remember, these are the values not in the domain. Let me set up a little number line because I know they're going to ask me for intervals. And I think it's a good idea to first have the graph. Here's my graph. All right, negative 2, positive 2. I'm going to put an empty circle here because I can't let x equal negative 2. I also can't let x equal positive 2. But x can be any value here that I'm going to highlight in red. So x can be any value other than these two circles. All right, well, this interval here is negative infinity, negative 2. This interval in the middle here I can write as negative 2, positive 2. And this interval over here is 2, infinity. I'm going to put a u in between, union, because it said enter your answer as union of intervals. Union means we're joining these three intervals together to get the final answer. So this is my answer for part A of this question. All right, let me go to part B. Part B says, this function, I'm going to set the denominator equal to 0. So for part B, I'm going to set the denominator equal to 0. Well, subtract 8 from both sides, x equal negative 8. This is a non-allowed value, so this is not in the domain. So again, let me do a number line here. Here's negative 8. And I'm going to put an empty circle here because I can't let x equal negative 8. You could probably see that when you look at this denominator. If x was negative 8, the denominator would be negative 8 plus 8. That would be 0, but that would get you in a lot of trouble because you're not allowed to divide by 0. Well, on this number line, x can be any value except negative 8. So this side I can think of as negative infinity, negative 8. This side I can think of as negative 8, positive infinity. Put a u in between for union. This is the answer for part B. All right, so this question was a little different because they asked you to enter your answer in interval notation, but I think it's a very good idea to draw a graph like this because then you can easily draw the interval notation just by visually looking at the graph. All right, let's do a few more. Let's go to number 9. All right, now number 9 is going to ask you to graph vertical and horizontal asymptotes. So let me give you a summary for this. For vertical asymptotes, so to find vertical asymptotes, what you do is you set the denominator equal to 0 and solve for x. What is a vertical asymptote anyway? Well, a vertical asymptote is when a graph gets closer and closer to a vertical line. Let's say this is x equal 5 here. So this vertical line is x equal 5. Well, a graph might do something like this. It might get closer and closer to this vertical line, but not touch it. So this is what we mean by a vertical asymptote. It's a vertical line that a graph gets closer and closer to, but doesn't cross it. All right, so all we have to do here is set the denominator equal to 0 and solve for x. So we got 4x plus 6 equals 0. Subtract 6 from both sides. So 4x equals negative 6. Divide both sides by 4. X equals negative 6 over 4. We can write that as negative 3 over 2. So I'm going to be graphing a vertical line, x equal negative 3 over 2. All right, let me come back in a minute and we can graph it. Actually, let me scroll down. Maybe I could do it now. Let me see if I could scroll down here. We need to graph a line at x equals negative 3 over 2. Now, if you notice, here is a dashed line for vertical asymptotes. Here's a dashed line for horizontal asymptotes. And this is going to let you plot a point. And so let me see here. If I do a vertical asymptote, it says enter the x and y coordinates of a point on the asymptote. Well, let me think for a second here. x equal negative 3 halves, right? That's negative 1.5. So negative 1.5 is going to be a vertical line like this. So I could pick any point on this line. I'm going to pick this point right here. I'm just picking at random. I could pick this point. I could pick this point. I could pick this point. I'm going to pick this point just to pick something that's easy to write. So this is negative 1.5, comma 1. And so let me enter that here. Negative 1.5, negative 1.5, comma 1. And I'm going to say draw the asymptote. And if you notice, it drew the red dashed line there. Let me clear the screen so you could see it better. All right, that's the vertical asymptote. Let's go to the horizontal. So vertical asymptote, you set the denominator equal to 0. Let me write that down one more time. Vertical asymptote for a graph like this. By the way, it's a rational function, we call this, where you'll have these kinds of asymptotes. Rational function just means a fraction. So when you have a fraction like this, you might have horizontal and vertical asymptotes. So to find vertical asymptotes, you set the denominator equal to 0 and solve for x. All right, horizontal asymptotes, they're a little more complicated. What you have to do here is look at both the top and the bottom. And what you want to do is compare the degree on top of the fraction with the degree on the bottom. And here's the summary. If the degree on top, let me make a little table here. If the degree on top is, maybe I should use N and M. So I think in the explanation, they're going to use the letter N for the degree of top, M for the degree on the bottom. Remember what degree is? Degree is the highest exponent you see. And so let me give you another example here to make it a little easier. Actually, I'll do another example coming up. But in this example, the degree on the bottom is 1. Why is the degree 1? Well, I'm looking at the highest exponent I see on x. Well, that's this, x to the 1. The degree on top, well, there's no x on top. If there's no x on top, the degree on top is 0. You can almost think of an x to the 0 being up there. Remember, x to the 0 is 1. All right, so here is this table I want to show you. If the degree on top, n, is less than m, then y equals 0 is the horizontal asymptote. If the degree on top is greater than m, the degree on the bottom, then there's no horizontal asymptote at all. Now, where it gets tricky is what if the degree of n is equal to the degree of m? Then you got to take the horizontal asymptote is going to be the leading coefficient on the top divided by the leading coefficient on the bottom. Let me do an example of that in just a second. But let's do our example. The degree on top is 0. The degree on the bottom is 1. Well, 0 is less than 1. So we are in this row of the table. So the horizontal asymptote is y equals 0. Well, y equals 0 is the x-axis. So let me scroll down. Let's draw that. If I scroll down, I want to click here on horizontal asymptote. And it says enter any point. Well, I'm going to enter any point on the x-axis. For example, I can enter 1, 0 and say draw the asymptote. And so you notice it put a dashed line on the x-axis. So that's the line y equals 0. All right, let me do another example where the rational function is a little different. So let me erase some of this, but I think I'll try to keep this table here. So again, folks, for horizontal asymptote, you got to compare the degree on top with the degree on the bottom of the fraction. Let me see. I think there was another one like this. Yeah. So let's do this one because this will be a good example. All right, it's going to say graph the rational function. Start by drawing vertical and horizontal asymptotes. So let's do that. So let's start off with the vertical asymptote. So we want to set the denominator equal to 0. All right, let's do it. Our denominator is negative x minus 2 equals 0. All right, I'm going to add 2 to both sides. So negative x equals 2, but I'm going to divide both sides by negative 1 to get x by itself. So it looks like x equals negative 2. So there's going to be a vertical asymptote at x equals negative 2. All right, let's do the horizontal asymptote. Well, I want to compare the degree on top with the degree on the bottom. This x, I'm going to think of as an x1, and this x is 1. So the degree on top here is 1. The degree on the bottom is 1. Remember, we call this n, and we call this m. Well, we're in this category then. The degree on top matches the degree on the bottom. To get the horizontal asymptote, you take the leading coefficient on top. That's the number in front of the x to the 1. So the horizontal asymptote here is going to be y equals 2. That's the leading coefficient on top. The leading coefficient on the bottom is negative 1. So this is negative 2. So there's going to be a horizontal asymptote at negative 2. Just a coincidence that the vertical and horizontal asymptote both turned out to be negative 2. Usually those will be different numbers. So if I was to come down here and graph this, let me erase, I guess, some of this stuff. Now that we did it, I think I can erase it. The x-intercept was negative 2. Excuse me, the x-asymptote was negative 2, so that's going to be here. The y, the horizontal asymptote was negative 2, so that's going to be here. Now, they're going to ask me to plot 2 points on each piece of the graph. Well, there's going to be a piece of the graph over on this side. I'll call it side A. There's going to be another piece of the graph over here on side B. What I could do now is I can just pick some random x values to plot. And so, if I picked, for example, x equal negative 6, that would be a point over on this side. So x equal negative 6. Plug into the function, get the y value. And then maybe I'll pick x equal negative 3. Get the y value. That would give me 2 points on the left side of the graph. Remember, there's a vertical asymptote here at x equal negative 2. Then maybe I'll pick x equals 0 and x equal 4 for the right side of the graph. And you can plot these points, and then you use this graph of function icon to actually graph. All right, so I just wanted to show, let me give you one more example of horizontal asymptotes. What if you had something like f of x equals 10 x to the 3 plus 9x to the 2 minus 6x over 2x to the 3 plus 8x to the 2 plus 10x plus 4. And the question is, find the horizontal asymptote. Well, I'm going to compare the degree on top with the degree on the bottom. The degree on top is 3. That's the highest exponent. So degree on top is 3. We call that n. The degree on the bottom is 3. We call that m. Well, it looks like, again, n equals m. So if you want the horizontal asymptote, take the leading coefficient on top divided by the leading coefficient on the bottom. In my example here, the leading coefficient is the number in front of the x to the 3. That's a 10. On the bottom, the leading coefficient is 2. So this would be 5. So y equal 5 is the horizontal line for the horizontal asymptote in this example. All right, let me do a few more examples here. I want to talk about inequalities. I think 16 was one. All right, so this one is asking me to graph the solution to this inequality on a number line. Really, they're asking me to identify any x values that make this inequality true. Well, here's what I'm going to do. I'm going to first start out to let this equation equal 0. Now, I know it says greater than or equal to 0, but I'm going to start out with equal to 0. Well, I could set each parenthesis separately equal to 0 then. That gets me x equals 6, x equals 1. I'm going to mark those numbers on the number line. So I'm going to put a 1 and a 6. Now, I'm going to make these filled in circles. Why filled in? Well, when you have a greater than or equal to, you should use filled in circles on the number line. If I just had a greater than symbol, I would be using empty circles on the number line. Our symbol is greater than or equal to, so I'm going to make these filled in circles. All right, I want to know the x values that result in this left side being a number greater than or equal to 0. Well, that really means a positive number. So what you do here is you say to yourself, let me pick this interval and see if this interval is part of the solution. And what you do is you pick a test point, any test point you want. Then I'm going to come here to this middle interval, do the same thing. Pick a test point. And I'll do it over here on the right side. Pick a test point. All right, I'm going to pick any number I want. I'm going to pick over here, maybe I'll pick -5. That's just a random number in this interval. Let me plug in x equal -5 into this inequality and see what happens. I would have -5 subtract 6, -5 subtract 1. Is that greater than or equal to 0? Well, this is -11 times -6. Is that greater than or equal to 0? Yes, it is, because negative times negative is positive. It would be 66 greater than or equal to 0. This is true. That means this interval is part of my answer. So I'm going to be coloring this in. So this is a yes interval. All right, let me go to the middle. I'm going to pick here x equal 4. Again, I'm just picking a random number in this interval. Let me plug that in. It would be 4 subtract 6, 4 minus 1. Is that greater than or equal to 0? 4 subtract 6 is -2. 4 subtract 1 is a 3. But this is -6. -6 is not greater than or equal to 0. This is false. That means do not include this middle section. It's not true. All right, let me pick one more test point to check out here. How about if I pick x equal 10 for this one? I'll do it over here. X equals 10. All right, I'm going to plug into the inequality. 10 subtract 6, 10 subtract 1. Is that greater than or equal to 0? Well, this is 4 times 9. That's 36. Yes, that is true. So yes, I want to include this interval in the answer. So folks, what you do here for these inequalities is first pretend the inequality is equal to 0 and solve that equation. Mark these numbers on the number line. Then go pick a test point in each interval that you see on the number line and plug it into the original inequality. See if you get a true inequality out of it. All right, let me do one or two more examples here. Again, doing these inequalities. All right. Well, I'm going to follow the same approach here. This one says x squared less than or equal to 4x. Let me get this set equal to 0. So let me subtract 4x from both sides to get started here. That's going to get me x squared minus 4x less than or equal to 0. Let me do a quick equation where I set this equal to 0. All right, on the left side, I'm going to factor out an x in front. That leaves me x minus 4. I'm going to set x equals 0 and x minus 4 equals 0. So I'm getting the two answers, x equals 0, x equals 4. Mark these numbers on the number line. Now, this is a less than or equal to symbol, so I'm going to use a filled-in circle here on the number line. If it was just a less than symbol, I'd be using empty circles. So I'm going to mark x equals 0 and x equals 4. All right, and again, I'm going to pick some test points. Let me see here. I'm going to pick x equal negative 4 as my test point here. I'll pick x equal 2 as my test point here, and x equal 8 as my test point here. Of course, you can pick any numbers you want in each one of these intervals. All right, and I'll use this equation to make things easy. Actually, we can use the original equation, I guess. X squared less than or equal to 4x. Well, here my test point is negative 4. So let me plug in. I got negative 4 squared. Is that less than or equal to 4 times negative 4? This is a question mark here. Well, this is 16. Is that less than or equal to negative 16? No, that's false. Right? 16 is not less than or equal to negative 16. So don't include this interval in the answer. All right, let me go to this middle interval. We're using the test point x equal 2 here. So x squared less than or equal to 4x. I'm going to plug in 2 squared. Is that less than or equal to 4 times 2? That's 4 less than or equal to 8. That's true. That means this interval should be included, so I'm going to highlight. All right, one more test for the rightmost interval here. Here we're using x equal 8. So x squared less than or equal to 4. 8 squared less than or equal to 4 times 8. 64 less than or equal to 32. That's false. So this is a no for this interval. So the only answer here with a test point that made the inequality true is this middle interval. So I would only be highlighting this part of the graph here between 0 and 4. All right, folks, let's see here. Let me do one last example. All right, well, this is the same setup, except here it looks like we're going to have 3 solutions. So let me start out setting this equal to 0 to identify the points on the number line. By the way, this is going to ask me to use interval notation. All right, well, I'm going to pretend this is equal to 0. I'll do it over here. So x plus 3 times x minus 1 times x minus 6 equals 0 to get started. That means each parenthesis gets set equal to 0. And that's going to get me x equal negative 3, x equal 1, and x equals 6. Folks, I think it's a very good idea to draw a number line for these problems. So negative 3, 1, and 6. Okay, and again, this is a greater than or equal to symbol, so I'm going to put filled in circles here. All right, let me do a test point in each interval. I'm going to pick a test point here of x equal negative 4. Here, I'm going to pick a test point of 0. Here, I'm going to pick a test point of x equal 3. And over here, I'll pick a test point x equal 7. All right, let's test each interval here one at a time. Now, let me give you a little shortcut. What you can do is just ask yourself, let's take x equal negative 4. Here is the starting inequality. Let me plug in negative 4 for x. Well, to be greater than or equal to 0, I'm looking for answers that are positive. Let's see here. This is going to be negative. I'm only going to think about the signs. I'm not going to work out the calculation here because all I really care about is the sign of the answer here. Negative 4 plus 3, that's negative. Negative 4 subtract 1, that's negative. Negative 4 subtract 6, that's negative. Negative times negative is positive. Positive times negative is negative. So this answer here is going to be negative, but we need an answer that's positive, right? Greater than or equal to 0 means positive. So this is going to be a no. Because if I plug in the test point x equal negative 4 into the original inequality, I get a negative answer, not a positive answer. All right, let me do the same thing with x equals 0. So if I plug in x equals 0, let me do it over here, x equals 0. It's going to be 0 plus 3, 0 minus 1, 0, subtract 6. I want to know, is this greater than or equal to 0, which really means, is it positive? Well, this is a positive. This is a negative. This is a negative. But negative times negative is positive. Positive times positive is positive. So yes, this is going to work out to be a positive answer. So this is a yes. So I'm going to highlight this interval. All right, let me do the other intervals quickly here to finish this one up. Let me do the next test point here is x equal 3. So let me plug that in the starting inequality. So I got 3 plus 3, 3 minus 1, 3 minus 6. Is that greater than or equal to 0, which I know means, is it positive? This is positive. This is positive, but this is negative. So altogether, this is going to work out to be a negative. That means this interval is a no here. All right, let me do one more example, one more test point, x equals 7. So let me plug in here x equals 7. All right, so x equals 7. So it's going to be 7 plus 3, 7 minus 1, 7 minus 6. Is that going to be greater than or equal to 0? Well, 7 plus 3 is a positive result. 7 minus 1 is positive. 7 minus 6 is positive. Well, this whole side is going to be positive, which means yes, it is going to be greater than or equal to 0. So this is a yes over here. So I'm ready to write my final answer now, because remember, they want this answer in interval notation. So let me write this answer here in interval notation. This interval is negative 3, 1. Oh, by the way, I got to use square brackets here because the endpoints are filled in circles. So I got to write this as negative 3, 1 in brackets like that. This interval is 6 comma infinity. And put a union symbol in between. Remember, anytime you write infinity, you always have to put a parenthesis with that. So this should be my final answer to this problem. All right, folks, hope this helps with things like asymptotes, inequalities here in Module 9. Thanks, folks.